There are objects in space darker than fresh asphalt. One planet reflects less than 1% of its star's light, and astronomers call that shocking. Picture a sky where a world makes night feel darker. This matters because darkness hides information, and that helps reveal exotic physics. Light hits these objects, and most of it never returns. Telescopes measure reflected light, and spectra show which wavelengths are absorbed. We compare reflectivity using a simple number called albedo. TR-2 billion, for example, has an albedo under 1%, so the immediate picture is. Space contains almost black objects, and they teach us new physics. A dense curtain of dust blocks entire starfields. Barnard 68 is a cold molecular cloud seen as a dark silhouette. This matters because such clouds hide the first stages of star formation. Gas and dust absorb visible light and scatter the rest, so the interior stays cold as it collapses. Observers use infrared and radio to peer through the fog, revealing protostars forming inside. Barnard 68 spans about a light-year across and looks like a perfect dark patch against the Milky Way. So the takeaway is, dark molecular clouds hide future stars. A gas giant so dark it feels like velvet. TR-2b reflects almost no visible light, and thermal emission dominates. This matters because albedo reveals atmospheric chemistry and cloud behavior. High-energy photons strike the atmosphere, and complex molecules and aerosols soak up visible wavelengths. Scientists use phase curves to separate reflected light from thermal glow, and TR-2b shows an exceptionally low reflectivity. It reflects under 1% of starlight, and that tells us its atmosphere is unusually absorptive. Net result, extremely dark planets expose strange atmospheric physics. Tiny, faint groups of stars hide massive secrets. Segue 1 is an ultra-faint dwarf inside our galaxy's halo. This matters because its stellar motions reveal a dominant dark matter halo. Stars orbit within unseen mass, and velocity measurements expose that imbalance. Segue 1 has only a few hundred stars, yet its mass implies far more dark matter. Observers measure stellar velocities to infer that mass, and the result is extreme. Bottom line, a handful of stars can betray vast invisible mass. A galaxy stretched thin, like a pale smear across space. Dragonfly 44 is an ultra-diffuse galaxy with few stars per area. This matters because such galaxies challenge how stars form inside dark matter halos. Stars are spread out and surface brightness is extremely low, so most of the mass hides in dark matter. Observers counted globular clusters to estimate its mass, and they found a huge dark-to-light contrast. Measurements suggest up to 1 trillion solar masses in dark matter, while visible stars number in the millions. So the image is, huge and faint galaxies can be massive yet almost invisible. A rotating cloud of gas can glow where stars do not. Virgo 21 is a candidate dark galaxy, seen as neutral hydrogen emission. This matters because a starless galaxy isolates gas dynamics and dark matter. Neutral hydrogen radiates at 21 centimeters, and radio arrays map its motion. The detected structure spans about 16,000 light-years, and its rotation curve suggests a coherent mass. Some work calls it tidal debris, and other studies keep it as a genuine dark candidate. In short, radio maps can reveal possibly starless, dark structures in space. A region so empty it alters cosmic maps. The Boötes void is a vast low-density zone with very few galaxies. This matters because voids change how matter clusters, and they test cosmological models. Gravity amplifies density contrasts, and voids expand faster than average space. The Boötes void spans about 250 million light-years across, and surveys of millions of galaxies reveal it. Voids shape the cosmic web, and their sizes inform us about cosmic evolution. So the point is, immense emptiness helps shape large-scale structure. A dark silhouette carved by gravity itself. The black hole shadow in MADI 7 appears as a central darkness framed by glowing plasma. This matters because the shadow tests strong gravity near an event horizon. Photons follow curved paths, and many fall past the horizon forever. The Event Horizon Telescope imaged a 40 microarcsecond shadow, and the ring shape matches general relativity. Observations constrain mass and spin, and they probe physics at extreme curvature. So the concise takeaway, black hole shadows are the ultimate astronomical darkness. Astronomers measure darkness in several ways, each revealing different physics. Reflectivity, obscuration, stellar scarcity, and emptiness are complementary probes. Each method uses specific instruments, from optical telescopes to radio arrays and interferometers. For example, albedo comes from phase curve photometry, and dark matter inference uses stellar velocity dispersion. Observations often combine wavelengths to build a complete picture, and cross-checks reduce false positives. The summary is simple: darkness in space is measurable, and studying it uncovers new physics and cosmic history.